Hello, Professor. I have one question that
Yes.
uh,
Yes.
yes, I have a topic number four for my term project,
Yes.
and there is a one other
Yes.
guy is also in that, but I find so many ways to like mail him or but I couldn't able to find his mail ID or anything, or I can't able to contact him to like for a working as a group. So if he is not responding me for anything, so can I make all the things by my own self?
Yes. You will both have to do an individual presentation if that is the case.
Okay, Professor. Thank you.
So the presentation should be about 10 minutes in that case. It's 15 minutes if you're in groups and 10 minutes if you're by yourself.
Okay. Okay. Thank you, Professor.
You're welcome. So today I just wanted to cover a little bit of the finite element method. And I don't cover much in this class because I just want to show the basic principles. There are courses that are devoted to finite element, and that's the main reason why I don't go in detail into it. I wanted to use this course more as a form of demystification, but if everybody does finite element, then um, maybe you don't see the broader picture and how they can all be used to do similar things in the end. Okay, so the purpose was really to cover finite element. And again, we're starting with the. I'm not sure. What is wrong? It always happens with your class. I'm so sorry. I spent the whole day online without issues. I do not understand why it's always in the evenings that suddenly something happened. And I restarted everything today, like even my computer before I started the class. I really have no clue why it happens to you guys every time. I'll be back shortly. I'm really sorry again. Okay, so as I was saying, I missed one piece of important. I'm sorry, I just forgot the key element for me. Uh, just to okay, just a little clock to let me know when we are, and I know if I need to speed up or keep going. So uh, as I was saying, so the entire purpose of this course was just to talk about numerical methods in general, and we saw how to solve some problems using the finite difference method, which is the simplest. And I was hoping, and if you understand how to fix some things for the finite difference method, then similar principles can apply whatever other method you're using. I'm sorry. But today we're just going to talk about this finite element method, specifically how it goes about solving problems, and you're going to see that particularly when we were considering the steady state problems, initially 1D steady state problem with the finite difference, we end up with very similar types of equations and matrix to solve as we had back in those early classes. So the finite element method itself, which again, if you want to go in more detail, there are definitely other classes that go into more detail in it. Dr. Martin Perez's class is on finite elements, so if you want to delve deeper into that specifically, I would certainly recommend her class to do so. Now, finite element method was first developed by both civil engineers and aeronautical engineers to solve specific problems, complex problems related to large structures or dynamic loadings as they had in the aerospace industry. And it's been used to model structures using small interconnected elements. I mean, the simplest kind of finite element structure you can think of is when you were solving, truss elements in your structured classes. I'm sure you have, if you have taken structured classes, you would have gone through truss elements and how you end up defining everything. So that basic concept summarizes the entire method thereafter. So each element in that concept is linked to all the others through shared nodes, or boundary lines or surfaces if you're talking to 2D, 3D. So you have these surfaces that connect them, the elements. But the nodes are where things are getting calculated at. Yeah, you have a question? No. I have a feeling that so you can certainly select this. So first you need to discretize your domain, um, and uh, oh, let me just check one thing. So first we need to discretize the domain, just as we needed to do it in the finite difference method, where usually we would have a grid. It doesn't need to be a regular grid even in the finite difference. But in finite element, you can more easily follow the shape of the elements. The specific grid in the back is not so much needed. And then you select the displacement function. that the displacement function, think of it, um, it's not required in the overall solving process. Okay, so the displacement function is an interpolation scheme that you use within the element. If you need to define a value at a given point within the element, this is where this displacement function comes into place. It's really an interpolation function within the element. Um, that function itself is not required to solve the overall problem. Then you need to define the stress strain displacement. So these are the constitutive relationships. This is what you need to solve. This is the relationships that in finite difference, for instance, this is what the equations we define in finite difference and we solve using the mesh. So this stress strain displacement, these constitutive relationship are the ones that come into play in the finite element to solve for the values at the nodes. So having defined these relationships, then you can derive the element stiffness matrix, and it tends to be called the stiffness matrix even when you're doing evaluations of say flow through porous media, things like that. You still use the stiffness matrix terminology because of tradition and the first problems that the finite element method was derived for. So you define the stiffness matrix for each element, and then your job is to assemble the individual elements into a bigger matrix. And then you introduce your boundary conditions, and then you can, once you have your boundary conditions, you can then solve, calculate your displacements, your reactions, and then as usual, what you have to do is interpret the results. Okay? So first step, discretize and select the types of element. So steps 1 and 2 are tightly related because the element types that you choose will determine the number of nodes, and based on the number of nodes that you have within a given element, that's what will determine the displacement functions that you will use for interpolating within the element. So you select the type and shape of the element, and what's important is that the element must be small enough to give useful results and large enough to reduce computational effort. And remember, although we don't have in finite element, we don't have a specific requirement as we do in finite difference, particularly in time dependent finite difference problems, where we need to make sure that when we're using the explicit finite difference method, we need to be sure that we are that the term 1 minus 2r is always larger or equal to 0, right? So that does not exist per se in this method, but it still gives you an idea when you choose a specific time step or when you have certain size of elements. It will still constrain you to the time steps that you can use. If you have a very, very fine mesh and you use very coarse, you have a time dependent problem and use a very coarse time steps, but you have a fine mesh, you're still, because as I was mentioning in terms of the finite difference, what that term represents is, think of it a little bit like the speed of causality. You know, the same way that you have a speed limit in in a vacuum, you have information cannot propagate through the universe faster than the speed of light, which is really the speed of causality, how fast information can travel through the space-time continuum. And the same thing, you have a maximum limit within a medium. You have the speed of sound within the medium. It's the speed at which a wave, so information, can travel within that medium. And that's basically what that term, the when we said that r must be larger than zero point 0.5, that's when we had 1D, right? It was really in 2D. It's the term 1 minus 2r, 2rx minus 2ry if you have in 2D, and minus 2r z if you have it in 3D, which must be larger or equal to 0. It's that whole term. Okay. Uh, and it's a little bit because of that. It's the speed of information travel within your medium that cannot pass that speed. So if you have a change that occurs at one node, and within one time step that you would need to do the calculation at the speed that things are moving through that node, it would be very far away, then it is no longer correct to assume that you can use the information on those two adjacent nodes, to determine what's the value or the changes within that element, okay, or that in the case of the finite difference within that those grid points, okay. It's a little bit because of that, because of the speed of information within the medium. It's equivalent, very close equivalent to the concept of speed of light being the limiting factor as to how fast the information can travel in the universe. Okay, so keep that in mind. Even when you're working with finite element, if you have a fine mesh, um, you may find yourself needing finer time steps to be able to solve things properly. Okay, when you have time dependent problems, of course. When you have boundary condition problems, then it doesn't matter. Um, Actually, while we talk about that and uh, talk about boundary value problems, so you remember that when we were talking about, say, pore pressure dissipation, uh, and we were talking about the finite difference. This is just to illustrate the point a little bit more. So we were saying, well, the pore pressure was basically R times ui minus 1 plus 1 minus 2r ui plus r times ui plus 1, right? That's what we had ended up finding. And then you remember when we were doing, where we were solving boundary value problems and assuming, the or change of water content over time was equal to 0, right? So we were saying steady state flow. And what we had ended up there were equations in the form h equals u I minus 1. Oh, okay, thanks. Thank you for mentioning. Let me make sure that I have the auto switch on. Okay. Yeah, because of the initial technical difficulties, I forgot to turn it back on. Thanks. So we ended up having our equations, right? And so hi minus 1 minus 2hi plus hi plus 1, right? Now, so you remember this was the case of the steady state? Okay. Now, just for the to examine a little bit more these statements. So we had defined already. Oh, you're still getting me? I seem to be. Okay. Okay, I'm sorry about that. I really don't know what's going on. No, I use the national. Well, that's not the issue. I've been having excellent connection all day. Uh, I use National Capital Freenet, which uses basically Bell's phone lines. Uh, no, no, it's not through Rogers. It's basically using the DSL lines that I'm using. Um, and it's something strange. It's just at this particular time. I'm not sure. It might have to do with yeah, it could have to do with the network itself, but it's strange. Um, so in any event, so I have this. So what happens? We said that R must be smaller or equal to 0.5. So what if we make R equal to 0.5, right? So this term here becomes 0. So what we ended up saying, sorry, what we had ended up saying is when we were doing in a uniform soil, right? We said that for each step we ended up saying that we had it was basically the average, the weight average, right? If we had K, then K would be coming here and we would have a weight average. At the limit, if it's a uniform soil, we add HI plus I minus 1 plus HI plus 1, right, over 2. That's what we ended up having for the case of the steady state. You remember? So if we have R equal to 0.5, in this case we have 0.5 times UI minus 1 plus 1 minus 2 times 0.5, so that whole term becomes 0, plus 0.5 UI plus 1. So in that case of R equals 0.5, it looks a lot like the iterations we were using for the steady state case. Okay, so what it tells you is that when we're not trying to solve the steady state case, because we saw two ways of doing it: trying to solve it with one matrix that we inverted, or we could have solved it by doing multiple steps. When we did it, solving this equation, assuming that Q that we have change of water content, so d theta over dt, so change in water content over time equals 0, right? We ended up with this equation here. And if you notice, if we set R is equal exactly to 5, we get the same thing, where u at time ui at the next step at the next time interval is equal to 1/2 of ui minus 1 plus ui plus 1 in a uniform soil. Okay, so we end up with exactly the same equation, which means that when we were doing it by iterations like that, we were automatically, by assuming that we had steady state to solve that equation, we were doing a time-dependent solution, but arbitrarily choosing the time step so that we would change things as fast as they could be changed within that medium. Okay, so I thought you might be interested in realizing that we came to these equations from two different angles. One was assuming that the change in water content over time to get to our consolidation equations was not 0, right? But we ended up with a general equation that when we set it to its possible limit, the maximum speed at which we can have things travel, we basically got the same equation as saying steady state, setting steady state as our equation and solving it iteratively rather than in one step through inversion of matrix. Okay. So I just thought that it was an interesting uh, detail to show you. So when we use finite element, though, we always go to the solution using inversion of matrix. Okay, so the finite difference has multiple ways sometimes to solve the same problems. In the finite element, you have to generate this matrix. You have to invert and solve for it. You do have to choose your elements wisely to optimize the computational effort and have a sufficient resolution in your problems. So you have different types of elements that you can use. For instance, in 1D, you can use a 1D truss elements or a beam elements. You can have bending, you can have compression, depending on which directions it can go. In 2D, you will use flat elements. The simplest is the triangle. And within them, you can do linear interpolation. You can use trapezoidal elements. As you add nodes, you end up changing the uh, the functions that you use to interpolate within the element. You can use prismoidal elements in 3D. Okay, tetrahedral elements being the simplest. As you add sides, then you add nodes, and then your interpolation functions are your shape functions are different. Of course, you can also do 2D that tries to be 3D, as in axisymmetric problems. So once you've chosen your elements, depending on the type of problem you have to choose to solve, the second thing you have to do is to select a displacement function. And the displacement function is chosen within each element. So as I said, that's an interpolation function within the element. You only need it in the end once you want to be able to calculate the changes within any element. It's like solving your finite difference problem and then trying to find values at intermediate positions. You might use an interpolation function to use the nodal values and calculate values anywhere in between. So then you have to define your strain or displacement, stress strain relationships. For 1D, for instance, you can define the linear strain as the displacement, the change in position over x or the direction, change in length, for instance, over the direction. And then you relate that to the stress using constitutive relationships. Again, for simple elastic deformations, your constitutive relationship is Young's modulus times the strain. So you define the strain in terms of change in positions in each direction, and then the stress is therefore the strain times the Young's modulus. Okay, so that's your constitutive. This is the constitutive relationship. And then you build the element stiffness matrix. There's different work methods to determine the element stiffness matrix. We're not going to go into details into all of them. This is very cursory, very brief overview. Okay, again, you have there's other courses that are concentrated on finite element, and so you really want to just breeze over. We were just going to breeze over these methods in this class, but there are different ways that you can generate your stiffness matrix, making different assumptions, and some are more appropriate depending on the type of problem you want to solve. So,
does these methods have any advantage over the other one?
yes, when you have finite,
Which are
when
better
you're
for technical?
Probably the worker energy, the way this one, the methods of weight residuals, I would say, is the most general application. You can, once you have a differential equation, it's the one that will generally allow you to solve for more types of problems. Okay, it's the more general way of formulating. Basically, you're doing the same thing in all cases, but the method of weight residuals, this is one that maybe you want to research a little bit if you want to implement finite element method on your own, because that one will allow you more.
Galerkin is one of the branches of this method. Yeah,
Pardon me?
Galerkin.
Yeah, yes, you have these methods exactly. So that's the most general. When you're specifically doing structural analysis problems, probably the direct equilibrium method is the more um, intuitive method to solve your problems. So the stiffness matrix basically relates the nodal forces to the node displacement. Okay, so you have a displacement in millimeters of the node that is tied to the force acting at that node. That's the essence of the finite element method. Okay, and so they will be related in the global sense. So if you have a list of all your nodes in your domain, you have a structure defined somewhere in space. Okay, so you will have nodal displacements. This is a 2D problem, obviously, although each element is 1D in the case of a truss, so it does simplify many things, but the displacements are still 2D. And so you need to relate the forces that act overall to the so you'll have boundary conditions at the boundaries and applied forces at given nodal locations. And then you'll have the general stiffness matrix that relates that to the displacements. So you want to be able to solve for the displacements, but also the forces that exist. Now, the direct stiffness method allows you to superimpose elemental nodal forces. And so you're able to divide things into the individual elements, and later on you can combine them to build the general stiffness matrix, the global stiffness matrix. So the basic assumptions to do this is that there's continuity, that the structure has no tears anywhere, and you need to introduce boundary conditions at some nodes. Otherwise, you have a singular matrix. You cannot solve it. Okay, the determinant is 0, and if you have a determinant equal to 0, it means that you cannot solve the matrix. So if you have n a total number of degrees of freedom, then you'll have to go to a matrix that is n by n, basically, because you have vectors of n elements. Okay, so that's all depending on the degrees of freedom are the number of nodes multiplied by the things that you're measuring at each node, right? So in this particular case of a truss, what you have is displacement in the y direction and displacement in the x direction. So you would have 1, 2, 3, 4, 5, 6 nodes times 2 degrees of freedom per node. So basically 12 global degrees of freedom. If you had beam elements, then you would have to also measure rotation, and so you would have another degree of freedom at each node. So you can get stress and strain from the node displacement, uh, and then from there you can interpret things within. Okay, so interpreting the results, that's important in all types of problems, not just for finite element, that's also for the finite difference problems, right? So if I give you a problem, whether you solve it by finite element or finite difference, right? I give you a dam. Maybe it has a clay core of some sort. And so you do an analysis of flow. You identify the ground or the phreatic line, right? And then the you can generate contour lines for your equipotentials, right? And they will be tighter. You have more head loss within the clay, so you will have all kinds of interesting things happening there. Whether, however, you've solved for that problem, interpreting what it means, interpreting what are the consequences of those, will be your job looking at the analysis. So whenever you have, say, equipotential lines that are closer, then you know you have higher head loss, you have greater gradients, and likely less flow, and the flow will tend to prefer the path that have less head loss, right? So same thing when you're dealing with stresses, you'll have to determine, look at the picture, look at the data, and identify what's more important. So usually you need to have some nice visualization tools for this step to be able to make the most of the information you get. So if we want to look at this, let's look, for instance, at 1D spring element. So this is the simplest form of a finite element problem. Okay, and in the case of a spring, then the spring constant is equal to AE over L. Okay, if you can imagine that you have a bar. Okay, so we can represent a bar if you have a steel bar like in a truss. But in this case, we're doing 1D problems, so you would imagine bars that are only lined up like this. It's a 1D problem. So you could represent the spring constant of a bar as AE over L. Okay. So the spring problem is not only good for solving spring problems, it's also good for solving bar problems. It's also good so if you have a bar in torsion, you can then use the polar moment of inertia and the shear modulus over L, and then you can model bars that are in line in 1D and then are being torqued. Sorry, I dropped my pen. So you could have bars in 1D and that you simulate how you torque them and have the torsional movement. So the spring 1D spring element can be used for other things than just springs. You can also do 1D heat conduction or hydraulic conductivity, hydraulic conduction. Okay, where again A is the cross-sectional area. This is the hydraulic conductivity or thermal conductivity of the material. If you're doing water problems, then it's hydraulic conductivity. And L is the element length. Okay, so you could compare that to your finite difference. 1D flow, Okay, so a lot of these problems can be solved in a similar manner. So based on that, so we can look at how we would solve for a spring, and knowing how we would solve for a problem with the spring, then we can generalize and solve for different types of problems. So first you need to, so if you go into the spring, you need to define a displacement function. As I said, that's your kind of interpolation function. Okay. So when you have only two nodes, using a linear relationship is the simplest type of relationship that you can use. And so you have the deformation is equal to constant 1 plus constant 2 times x. Okay. And the total number of coefficients c is equal to the total numbers of degrees of freedom of the element. Okay. So basically the displacement is based on the relationship. So you have 1 x, so x at any position along the bar times the vector made by c1 and c2. Okay, so how do you define? So you need to define your displacements, or your function u at the nodes. So you have two nodes. You can be either at 0 or at L, where L is the length of the element. So at 0, you know that x is equal to 0. So x being the position along the element. And so the C1 is basically equal to the displacement at the first node. Okay. Similarly, if you replace x by L, then you know that C1 is the displacement at 1, and so you can determine C2 is the difference in displacement, okay, divided by L. So C2 is basically the strain of the element, assuming that you have a constant strain within the entire element. And so you can rewrite the overall equation as d1 plus d2 minus d1x over L, and you can rewrite it in terms of the nodal displacements themselves. Okay. And so this is your interpolation little element that you have within. So you have x over L times displacement 1 and displacement 2. So n1 and n2 are your shape functions, and in the case of the 1D spring element, you have n1 1 minus x over L, and n2 is x over L. So basically one is measuring that direction, the other one the other direction. So what is the constitutive relationship that you can use in this particular case? Obviously your constitutive relationship is the tension in the spring.
You are breaking up a lot.
Okay. Let me see what I can, if I can do something. I'm not sure what to do. Let me try something. I will come back shortly, see if it improves things. Just a sec.
cannot see it.
Oh, you cannot see?
Yeah, now we can.
Okay. You have the spring constant times the difference in displacement between the two ends, which is delta. Okay, so you have the difference, so displacement at L minus displacement at 0. So it's basically the difference in those two displacements. And so in this case, d1 is negative sign and d2 positive sign, because they're in opposite directions. Okay, if in the particular model. And so you have the sign convention, so you have minus t at the first node and plus t at the other node. Okay, so we have both the tension and the displacement, which is the difference between the two nodal values. So you replace that into the equation. So at the first node you have minus f1x, which is the reaction or the force at the first node, so it's equal to the tension, and so it's k times the difference in displacement. And at the second node you have k times the displacement difference. Okay, so what changes that? Obviously we have d1 minus d2 and d2 minus d1 when the values are, so here we had minus f1 and this one we have f1. Okay, so that's why we ended up inverting the two signs. So if you express it this way, then you're relating now the nodal forces f1 and f2 to the nodal displacement through the spring constant, and so we have here our constitutive relationship. Okay, and having our constitutive relationship, what we have, this is our stiffness matrix. Okay, k minus k minus k and k, and again that could have been the in the case of the hydraulic conductivity, we were looking at pore pressure related to pore pressure was related to the or the flux related to the pore pressure, right? So instead of force you get flux, and instead of displacement you get hydraulic heads. Okay, and you would get the same kind of relationships. Okay, so we have a symmetric square matrix, and then we can solve the global stiffness matrix by assembling them into the so we would assemble them based on their nodes. So in terms of the nodes, oh, I'm missing a part here. Just missing an important window for my use. Okay. So if we have a set of nodes, so this is node 1, 2, 3, 4, that's element 1, element 2, element 3. Okay, so we need, so for element 1 we have, looking back at our equation, So what did we have for element 1? Well, we have node 1 and 2. So we have obviously K1, K2, K3. And so we would have these two values there. And so what would it be equal to? It would be equal to K 1 1 1 K 1. What is it for element 2? For element 2, we're joining node 2 to node 3. So we have F2 and F3. K2 minus K2 minus K2, K2. And finally, we have element 3. We have nodes 3 and 4. We have K3 minus K3 minus K3, K3. And so the global stiffness matrix will be depending on the external forces on F1, F2, F3, F4. Oops. Right, and so now we have to find the element. So F1 at 1. We look at F1. We have K1, right, with respect to D1, and then with respect to D2 we have minus K1. So that's what we're going to look now, how we assemble these things into the global matrix. Okay, it's going to be faster if we look at this example, but we're basically going to add the values from the different elements. Okay, so we had K1, so with F2, and so this means that we have F1 K1 D1 minus K1 D2, right? But if we were looking at F2, okay, F2 was equal to minus K1 D1 plus K1 D2, and F2 was also equal to K2 D2 plus minus K2 D3. So if you have here your nodes, you have displacement 1, displacement 2, displacement 3, displacement 4. And so for the global, so this is in terms of D1, D2, so on. So you have here for D2 and F2, so you would have minus K1 for D2, so it's would be plus K1 plus K2, but it would also have as a function of displacement 1 minus K1 times displacement 1, and then in terms of displacement 3 minus K2. Okay? So you end up with a matrix like that with elements from all of them. So what does it mean in terms of an example? Let's assume we have a set like this where we have two springs with spring constant K1, spring constant K2, spring constant K2, and we need to solve the problem where we are applying a force at F2 and a force at node 3, and at node 1 we don't know what F is, but we know it will be the reaction. If I had no force at F3, I could set F3, the external force is equal to 0, so I could have external force equal to 0 anywhere, but those are going to become important later on. So element 1, remember element 1 is, so we have node 1, node 2. Obviously the number of the nodes doesn't have to be sequential, okay? That's what we're trying to highlight in this example, because obviously when you have elements in space, there's not only one way that you could follow to number them, right? So you could have the numbers in any organization. It's just important to know which one is related to one. So for the first element, you have K1, but it relates node 1 and node 3, which is important to know. So we have node 1, node 3, F1, F3, and we have element 1, so we have the first spring constant. And it's just K1 minus K1 minus K1, K1. Simple. For element 2, same thing, except that this time we're going between element 3 and node 3 and node 2. So we're going from node 3 and 2. Okay. So compatibility requirements means that D3 for element 1 is equal to D3. So there's only one displacement at D3. Okay, because we have the same displacement between the two nodes, the two elements. Okay, it has to be the same value. And so node equilibrium means that F1 is equal to the element F1, global F2 is equal to the element F2, but global F3 is equal to the sum of both element F3. Okay, and so we express them in this general fashion. So F1 will be equal to whatever we have there for F1. So there's only one term with F1, so it's K1 minus K1, D1 and D1 and D3. Okay, so this is F1, this is F2, okay, because F1 is equal to K1 D1 minus K1 D3. K1 D1 minus K1 D3. F2 is equal to minus K2 D3 plus K2 D2, minus K2 D3 plus K2 D2. F3 is equal to minus K1 D1 plus K1 D3 plus K2 D3 minus K2 D2. Okay, so this is the term that we have here. So it's basically just expanding the stiffness matrix. And so we replace those. So if we order these D1, D2, D3, we just place the K values where we needed them to be. Okay. And so this is our global stiffness matrix. Call it global. That's how we usually refer to it. Okay, so we can use the so in terms of direct stiffness, we can just look at our individual stiffness matrices. Okay, this is the direct stiffness method, and so we add, so whenever so this belongs to node 1, this is node 3, so at node 3 we will be adding the same values. So D1, D3, D2, D3. So for element 1, it means that we have 0 in turn. So element 1 only depends on, so we'll call it this way. So let's build it here for element 1. Right? Element 1 only has nodes 1 and 3. Right? And so, but our final matrix, we know will have nodes 1, 2, 3. So, but still, F1 has, in terms of D1, it has at K1, and then it has the K3, right? And so in terms of D1 here, we have minus K1, and then K1 for D3. Zeros everywhere else. Okay. So that's D1, D1, K1. D1, D1, K1, D1 and D3 minus K1, D3, D1 minus K1. Okay, so for F2, same thing. 1, 2, 3. Position 1, 2, 3. So here we have 2. This is 2, 3. 2, 2. So that's K2. 2 and so position vertical 2 and 3 minus K2. Then we have 3 and 2 minus K2 and K2. And everywhere else we should have zeros, right? So that's what we have here. Okay. That's basically how we build those matrices, and once this is done, because we are organized 1, 1, 1, so I can have my global stiffness 1, 2, 3, 1, 2, 3. So position 1, 1 is this plus 0, so K1. Position 2, 1 is 0 plus 0, so it's 0. Position 3, 1 is minus K plus 0, so minus K1. Then 1 and 2, 1 and 2 is 0 plus 0. 2 and 2 is 0 plus K2. 3 and 3 and 2 is 0 plus minus k2, and then we have minus k1 plus 0 minus k1 minus k2 k1 plus k2. Okay, so we just assemble them that way, and of course we can take out each of these values if we want, but we now have to consider the equilibrium of each of these functions. Okay, so we have k1 times the initial matrix times deformations, or we just assume the global stiffness matrix. Okay, so forces, the combined forces must be referred to the resulting values. Okay, and so what we know is that d1 must be equal to 0. Okay, that's one of the boundary conditions. We know that the first node cannot move, so we set this one value equal to 0. And that's a fixed end. We also know that f2 and f3, so because of that we can remove first row, first column. Okay, this row and column are known, so we can remove those from the problem, which leaves us with our two known functions. We didn't know this value, so we were able to get it out of the equation. And now all we're left is with the two known forces. Okay, potentially this could be 0 if we had no value there, but what we have to do basically is find the inverse of this matrix, multiply by the known nodal applied external forces, and that will give us the displacements. Okay, so now we have the displacement at each location, and then we can go back and find our nodes. Once we have all the displacements, we can go back and find the reactions at each of the intervening forces. Okay, so basically we can express so this is just resolving it algebraically, but we would have been able to resolve it numerically otherwise. Okay, so now we'll do another example with 3 springs, and this time we're confining nodes the two extreme nodes are being confined. We have 2 springs with each their own material properties, spring constants, and we are applying a known force at node 4, and we want to know what are basically the deformations but also the reactions at the two ends. So we do the same thing. So we have the nodes, we indicate which nodes, okay, can be helpful to keep this in check. So we have to build our global stiffness matrix based on these. So if we have 1, 2, 3, and 4, okay, 1 will only have 1,000, 1, 1, and then we have 1, 3 is minus 1,000. Okay, and then we have 1 and 3 down, 1, 2, 3, so this one will be minus 1,000. And 3, 3, 1,000. Then we go to element number 2, which is 3, 1, 2, 3, and 4. So we go to 3. Oops, that's 3, 4. That's 4 and 2. So 3, 3, 3. So we have 2000. So 1000 plus 2000. Okay, so that will be 3000. Then we have 3, 4. That's minus 2000. 4 and 3. 3 and 4 will be minus 2000. And 4, 4 was 2000. Okay, then we go 4, 4. So 2000 plus 3000. 2 and 4, it's minus 3000. So that's 2 and 4. And then we go back to 4 and 2. 4 and 2, it's minus 3000. And 2 and 2 is 3000. And the rest should be 0, 0, 0, 0. So 2000 plus 3000, 2000 plus 3000, 1000 plus 2000, 1000 plus 2000 minus that. So you see there's all the values that we had there, and this is how we would build it from the matrix we have there. Okay, so this gives us our stiffness matrix, global stiffness matrix. Okay, we express the force at each of the nodes with respect to the displacement at each of the nodes. We also know that at nodes, what was it, 1 and 4? 1 and 2, okay. 1 and 2, we have 0 and 0. Okay, so 3 and 4, 3 and 4, we have 3 minus 2000 and 2000, so right, d3, d4, and so we find the inverse of this matrix. This one was 0 and 4, 5000. Okay. So that's 0 and this is 5000. So we have the inverse times 0 and 5000, which will give us the displacement function. Okay. And so we can express that in terms of their values. So we have displacements d3 and d4, 10/11 and 15/11 of an inch respectively. And if we put that into the overall system, we can find the reaction at 1 and the reaction at 2. And so that's the direction of the force. So the force is going positive in that direction. So it means that the reaction at 2 is in this direction. And similarly, the reaction at 1 is in that direction also, which means we have a tension here and a compression there. Okay, so that's the direction of the force in absolute terms. So you can find then your reactions at each of the individual nodes if you want. And basically that's how you solve these little problems. Okay. Does sound straightforward so far? So you can probably material models. Okay. So now we're just going to briefly talk about the so if you use sigma W, you will find that you have different material models that are used internally. So sigma W is the finite element component of for mechanical behavior of the GeoStudio, right? So we talked a little bit of CW that solved for seepage. Sigma W solves for mechanical components. You have Quake that will solve for dynamic, so earthquake, for instance, loads. So what are the material models that it has? Linear elastic, which is the simplest, obviously, model to use. You can use an anisotropic model, which means that you will have different properties in different directions. So it will not be the same modulus of elasticity in all directions. You can have a nonlinear elastic, usually the hyperbolic model, where you have an asymptote, which is your maximum possible strength. And then you have the general elastic plastic, which needs to, so when you're going into plastic deformation, you need to take into consideration the history of the material. So the moment you talk plastic, you have to say, okay, what was the maximum strain in that element that I ever reached? Because if you unload, you follow elastic, but if you reload, so you have to continue from where you were, right? So the strains build up. So in terms of the elastic model, it's just relating stress strain linearly, okay, using Young's modulus essentially. And so what you need is Young's modulus, but you also need the Poisson's ratio, because when you're deforming mechanically a component, so you apply loads, and this is the main difference between stress analysis and, say, things that we have seen like water pressure, where flow through porous media, we had Q, which is a vector and only dependent in each direction on changing a difference in head in each direction, right? Right, times J, etc., etc. So it's separate, but here we are linking the Poisson's ratio. Basically, links the stresses between them. So here, instead of talking directly about the force and displacement, we're linking stresses to strains, and we have the axial strains and the shear strain. And this is the constitutive model that relates them. And of course, this is the stiffness matrix that you have to use in that particular type of problem to relate the values. Okay? But again, you can combine those. So technically this should be multiplied into each of those terms. So when you calculate the terms in your matrix, the elastic modulus will definitely be part of the overall combination. Okay. In an isotropic model, as I was mentioning, you should consider the difference between the elastic component in the x and y directions. Right. And obviously, there's ways that you have to consider the stresses in different directions. Okay, so we already saw how to do the rotation of the systems of coordinates. So hyperbolic model assumes that as you approach a maximum value, okay, so you can you will basically have, so your elastic modulus is not constant but is a function instead is a function of the stress in this particular case. Okay, so in practice it is a function of the strain, but the elastic model things are simplified. The hyperbolic model things are simplified, and what you're saying is that you follow this. You're assuming loading going in one direction basically, and so you're relating that to these terms. So you have the normalizing atmospheric pressure, and this is just a way to reduce this to a non-dimensional value so that you can apply the exponent, and the atmospheric pressure here returns this to a dimensional value in the end. So n will often be the square root in this particular problem. And the tangent modulus is the modulus at any location, which will depend on the friction angle and the initial tangent modulus. Okay, so that's the model that is used in sigma W. So you cannot model dilation under shear stress. You cannot model strain softening. So you cannot have curves like this, which are very typical of various types of soil. And obviously you're not taking into account the effect of the intermediate principal stress. Then there's the chem clay model, which is used internally for several types of clays, and it introduces different parameters based on the compressibility, the compression index of the soil basically. And those are the models that are used internally in sigma W. Okay? So we will take a break here, and after the break we'll go over a few of the different types of models that we can apply, the equations that we've seen in the past too, and we will conclude the lectures on those notes. Okay. So let's just take a little break here, go drink some water, maybe go to the potty, and we'll meet back in 10 minutes.
Okay.
Hello again.
Hello.
So, um, I want to conclude this course and this lecture just by going quickly over other types of problems and numerical methods that are applicable in geotechnical or even geoenvironmental engineering, where you can use numerical methods to solve problems. And you will see that many aspects of these types of problems are very, very much very similar to actually the problems that we've solved in the past. So first one will be the thermal analysis, because that's actually the more complex. It has some aspects that are extremely similar to seepage problems, but it adds some other elements into it. So if you're talking about convection and conduction and radiation. So basically, in these types of problems, the temperature changes in the body, they can cause expansion, contraction, so they can definitely have also mechanical effects into these bodies. So the type of modeling that you can do can start combining different types of analyses into a more complex setup. In thermal analysis, you could also have problems that include phase change, like freezing water or melting ice. Um, and so that changes so many other parameters, right? From thermal conductivity to hydraulic conductivity to mechanical stresses and strains. Things can change very drastically. Just the temperature change could cause fluid flow because it changes density of fluid, and so it might generate through convection um, changes the flow in the fluid. Okay, and the thermal properties themselves of the materials can change. So thermal problems can become quickly very complex. And so, where are examples of problems where we would want to consider these things? Where obviously, in terms of frost penetration below cleared highways, we want to know how deep. So we can model using temperature models of the environment and see how far down the ice formation can go during winter, because we can have heave caused by the expansion of the ice. Uh, so if we have a freezing pipe, there will be a formation of a ice bulb, right? And either when it forms or when it melts, it can cause problems. Around the shaft excavation, we can also have formation of ice or melting of permafrost, thawing of permafrost beneath structures, freezing around the chilled pipeline. That can be an issue also sometimes. Okay? So what's important to know is that we have very similar problems, but and different types of analyses, but the independent variable is usually what changes the most in these types of problems. So in stress strain problems, the independent variable used to develop finite element models. So what was the independent variable we used earlier today to work on the model? We had the deformation for the spring constant, right? So in terms of stress strain, then the strain would become the independent variable. In seepage problems, what was the independent variable we used when we were doing uh, seepage problems? You remember?
The conductivity.
No, the hydraulic conductivity is the material property, but it was definitely the hydraulic head. And so what do you think the independent variable will be when we do heat transfer problems?
Temperature?
Temperature, obviously. So it's and temperature will affect conduction. It will affect convection because it changes the density, and radiation aspects of it because the amount of heat radiated depends on the temperature. The higher the temperature, the higher the heat radiated. So conduction refers to the flow of heat through the solids, so within the material. Uh, and so it's through the collisions of molecules and free electrons within the matrix of the material. Okay, that refers to heat conduction. Convection is a function of currents that exist. There might be currents induced by changes in density or existing currents. Say you have water flowing around a pipe that is chilled, or maybe a heat pipe. It can take away some of the heat because you will have, through conduction, you will have heating of the water in contact with the pipe, but through convection, that heat is taken away with the flow of the water. So that would be a case of forced convection. When you have a natural flow of water, that's forced convection. Natural convection is because of the heating process itself, which will cause expansion of material, change of density, and that will force also a flow. So there's two different kinds of convection. Radiation itself is emission of electromagnetic light, okay, waves through light. It can be infrared. Most of the time it's in infrared. If it gets hot enough, then it can go into the visible spectrum, and you definitely don't want to touch it at that point. It, it can be quite painful. Okay, and obviously through radiation, the energy transfer is at the speed of light. Or again, more than the speed of light, as I said before, it's the speed of causality. That's why the speed of light is indicated as c in the equations used by physicists, and c stands for causality because things, that's the fastest you can go to have a reaction to something. Okay, nothing can, no information, no causing element can cause a reaction in something else faster than that speed. So it's the speed of causality that we commonly call the speed of light. So there's typically two categories of heat transfer problems, like in most cases. So you have the steady state flow problems and transient heat flow problems. We'll start looking at how to develop the equations for conduction, because you will see that it has many commonalities with seepage problems. Okay, so in terms of heat flux, we use the same variable as we did with the same letter as we did for Darcy flux, right? We call it Q also in this case. Okay, and like the Darcy flux, it's minus K times a gradient, and instead of being the hydraulic head gradient, it's the temperature gradient in this particular case. So the flux in the x direction, and of course this is a vector term, okay, and so it depends on the thermal conductivity in the x direction, which may not necessarily be isotropic. Do you know a specific material that is Very, very conductive and very, very anisotropic. I think it's the most conductive materials of all. Would you have an idea of what this amazing conductive material, thermal conductivity, in terms of thermal conductivity? And extremely anisotropic. No idea? You give up? Graphite. So graphite will have, it makes thin sheets, so it will have different thermal conductivity along the sheet as across sheet. So if you pack it nicely, you will see that it has very, very different thermal conductivities. And so that can be used to, so it's important to know when you're doing your model, but definitely assuming isotropic conductivity in all cases should not be done for all materials. So if you're going in 3D, as I said, Q is a vector. So if we can also have a tensor here, and it's in terms of the gradient. Okay. So we have a negative term here because if we go from high temperature to low temperature, so from large number to small number, okay, that's the flow we get. So that's why we have a negative, because we don't go from small towards large. Okay, that's the implication of the negative on this value. It is the same thing as the negative that we have in hydraulic conductivity. So the thermal conductivity, one thing that you should remember is that a little bit like the hydraulic conductivity, it is not constant. It is related to temperature, a little bit like hydraulic conductivity is related to the water content, which itself is related to the hydraulic head, right? So if you have negative pore pressures, which is basically related to elevation head and hydraulic head, then you will start changing your hydraulic conductivity. And same thing is kind of happening with thermal conductivity, which changes with temperature. It sometimes can be small over a significant range of temperatures for some common materials, but in other cases it will vary a lot. In non-uniform materials, K will vary in space, and it can be useful to, so sometimes you can use this property to do simulations of different thermal conductivities along the material. So thermal conductivity can change with orientation. As we said, it's not isotropic, and so we will use a second order tensor. So let's imagine that we have a 1D element. Okay, let's consider it only in one direction. We have energy coming into our element and energy leaving out, just as we had water content changing. So the change in energy is equivalent to our change in water content that we had in hydraulic problems. So energy in plus energy generated, because sometimes you can have a generation, so you can have a source term. And that was true also in the hydraulic. We have kind of skipped the source term, but it's something that could exist within a given material. We can insert a source. If you have a point source somewhere, we can put it at any given node or given element. So the change in energy of the element plus energy out will be equal to the energy in plus any energy generated if you have a source or consumed if you have a sink. Okay, so and so the change in thermal energy per unit of time can be expressed as del Q over dt, the same way as in terms of water content we had d theta over dt was equal to change in hydraulic flux over dx. Okay, so you remember that that equation. Well, it's the same in this particular case, so in 1D or 3D. Okay. Um, but now we need to define the thermal capacity, which is the amount of energy that is transferred to an object for a given temperature increment. So something that has a high thermal capacity means that we need to apply a large temperature differential to have so it can store a lot of energy. Okay, so you need to apply a lot of temperature to an enormous amount of energy to get a measurable change in temperature. Okay, so the larger the value of C, um, it means that you need to have a very large increase in energy to have a measurable change in temperature. And so that should actually be delta Q over delta T. So we can generally express it as dQ over dt. Okay, so you may often want hear that water has very high thermal capacity. It's one of the best materials in that sense in terms of thermal capacity. There's very few, and certainly I don't think as common as water is. So water is has many unique physical properties that make it unique in the universe. It's common, made in part with well, the most abundant element being hydrogen. It has excellent hydraulic or thermal capacity. And so in terms of energy storage, that's why you will often see solutions that involve water to store energy in one way or another, okay? Because it's very good actually at that. So the change in energy is equal to the thermal capacity times change in temperature. Okay, that's an important little relationship that we can apply because it means that we can convert our term dq over d time as c d temperature over d time. Okay. And so temperature is now a function of temperature because temperature, the temperature gradient affects the thermal flux, right? Okay. And that means that we have this term here in terms of temperature itself. And as you'll recall in our consolidation problems, that made for a very nice equation. So we now have the term thermal conductivity divided by thermal capacity. Okay. That relates temperature to itself, basically, in a differential equation. Okay. We now define a new term called thermal diffusivity, which is K over C. And doesn't that look a lot like right, that we had for consolidation?
Yeah.
So it's exactly the same equation. Okay. So if you learn to solve the one, you can use the same exact same equations. You just change what the variables are, and all the methods that we've seen till now will let you solve for thermal problems. Okay. You just change the boundary conditions that you will use. So in terms of thermal conduction, what would be the boundary conditions that you could have? So I have a thermal domain. Say, so I can have controlled temperature. So I may have a hot side here and a cold side here. And I may have a insulation. Okay, and the insulation would be what kind of boundary condition if it's a perfect insulation?
We don't have a flow light.
Exactly. No flow boundary. So mirror, mirror, and then here you can control temperature. You can control temperature there. If it's temperature controlled, then you can determine. It might not be temperature controlled. Maybe you have a fixed airflow that can take away a certain amount of energy. So then you can use convection and things like that. In terms of boundary conditions using convection, radiation, etc., etc. Might become a bit more complex because you might say, oh, this is a radiation, we're in space, so this is a radiation boundary condition. So based on temperature, I lose energy at this rate, and therefore that becomes the boundary condition there. So in terms of boundary conditions, you start playing with parameters at that point. Okay, but that's how it would change. Okay, so this is the equation in terms of diffusivity that you would have. And as you see, it's exactly the same equation that we had for um, consolidation. Okay. Now you can also have the thermal capacity. And the capacity to store energy based on the volumetric heat capacity, which we measured before. Okay. But it's also a function of the latent heat content. Okay. And this is if you have a phase change, so you may be melting or freezing, evaporating. So in that case, you might express that in this term, which will complexify the changes. So at steady state, what you have is the same amount of heat flux going in and going out. So if you have boundaries in that sense, you can definitely control by applying fixed temperatures here and there. If you apply fixed temperatures, then you can definitely have a steady state flow. So the GeoStudio can let you do heat transfer problems through the TempW interface. So GeoStudio has many. It's available in the computer lab. I think we mentioned it in the past, if I'm not mistaken. And it has CVW that lets you do flow analysis, and you can combine the result of one into the other, and also into sigma W that does stress analysis. So you can combine all these different aspects to solve for complex problems. So the convective heat transfer, that's something that in TempW they use more as a boundary condition. They will not necessarily simulate convection within the soil, but you can have soil that is in contact with air or with a liquid, and there you will express a convective capacity to transfer heat away. Okay? And so you have a heat flux that will be calculated at the boundary, which will be dependent on H, which is a convective heat transfer coefficient for the process. And it depends on what process you need to emulate. You may have to do some separate simulation or go to literature. Say if you have a wind of this speed, this is the amount of heat it can take away for a given difference in temperature between the say if you have a surface that you heated, the boundary of your soil is at a given temperature, and the air is at say minus 30 degrees Celsius, and your soil is at 8 degrees. So how much heat is being lost? Well, it depends not only on the temperature of the air, but also on the wind speed, right, and things like that. So these are all factors that will come into play in this parameter h. So you have to have some idea of the process and how that process will convert a difference in temperature into a flux. Okay, so it's not necessarily as straightforward as you might first think. So it's worth thinking about it. Now, in terms of temp W, the equations that it uses are listed here. Okay, so as you can see, there's definitely different things that you need to take into account. I don't want to go into the detail, but just if you're interested in using these software in your own projects, it might be good to have some idea. Now, in terms of radiation, notice that the flux is a function of the fourth power of the temperature. Okay, so the more you increase the temperature, the more you increase the energy lost through radiation. Obviously, the Stephen Boltzmann constant is very small. It's to the power minus 8. So it takes a large temperature before you start having a significant flow of energy through through radiation, right? So that's why at the temperatures we're usually used to dealing with, conduction and convection are usually more efficient. But definitely, if you're in space, those are not very useful because you don't have much material in contact with the surface, so you won't lose heat through conduction or convection. And that's why heat dissipation can be a problem for space habitats. But once you get the temperature that is high enough, then you definitely get potentially a very high energy loss through the temperature difference. So what's the emissivity? The other variable that you use for this? Well, okay, here we have the thermal conductivity and volumetric heat capacity of different materials. So we have the for fresh snow. So these are typical values that you can use in your calculations for conduction. This is definitely for conductivity problems. Now, another type of problems that you may want to solve are an environmental engineering concentration of contaminant problems, right? And in those problems, then we use Fick's law. And Fick's law relates the diffusive flux to concentration, so the diffusive flux J to the concentration of solute under steady state. Okay, that's okay. Does that look familiar? so far? So phi is the concentration, d is the diffusion coefficient, and that's the diffusive flux. Uh, of course, concentration changes over time, and the concentration is a function of the diffusive flux in a given direction. So that's Fick's second law. And wow, does that look familiar? Does this look familiar? Oops, that's supposed to be plus, not times, but plus, because it's a gradient. Okay. So what you will find out is that there's many models that look the same. So we have Darcy's law, where we relate Q to right, heat transport. We had Q equal a Fick's law, it was called J. And in Ohm's law, I'll have to check the variables, but it's basically charge transport, and it's the same basic equation. So in all those types of problems, you have exactly the same equation, and so you already have the tools to solve for them. Okay? So with the tools that we've seen in this course, although it may look that we've done a lot of the same type of problem solving, when you look at the different models that you can have to solve for, you can realize that, wow, you have tools to solve a whole class, like several types of different problems involving different physical phenomena. Okay, so I hope you feel a little bit better about everything that we've seen, and hopefully you feel less scared about solving numerical problems. Any questions?
Yeah, if we want to solve these problems like heat transfer or hydraulic conductivity with FEM, to get that matrix, do we need to use, is it possible to get that matrix with virtual work principle or something like that?
Yeah, you could use it either way. As actually, if you remember, let me just find that slide that we saw earlier. Uh, oops, I think I need to close something. Yeah. Multi-view. Let me find the slide that we saw earlier. You can definitely use energy methods, but even as we saw also for the for previous problems. Oops. Right, so we saw it for torsion, But for heat conduction, uh, if you have the thermal conductivity, you can express the spring constant, or if you have a hydraulic conductivity, so the same way that we have these. So this is in 1D, but the concept is applicable in multi-dimension. Um, okay, so you have thermal conductivity, you use thermal conductivity here, okay, and you can have your stiffness, your K coefficient there. Okay, so you can change how you express your spring constant in the different types of models. Okay, so if you know the area of your element, cross-sectional area of your element, and the length of the element, then we can simply use this relationship and find the equivalent spring constant, and so we can calculate our stiffness matrix based on that. Oh, I think we were cut off. Are we back? Can you hear me now? Oh. Can you hear me? Apparently I left you guys again.
Yeah, I lost you.
Okay, let me fix the chat window. Okay, so as I was saying, so you see that you can actually define the stiffness matrix, right? In these types of problems, you can easily redefine it in terms of the material property. So of course, if you were looking at different directions, you have to be aware that you're talking now about x, y, so you'd have to look at the uh, y, z area and Lx and so on. So if you were doing it in 3 different directions, right? If you have an element that is a cube and you want to look at the flow in different directions, you have to look at so the direction L in the x direction, and then you would look at z and y, so the area of this, okay, perpendicular to the direction Lx, and then so you could define this in each of the independent directions. Okay, and that's how you would handle those problems. But for the rest, once you have defined, so you have qx is equal to uh, so you have your qx, you have your definition in this way, and so you relate that to h at any given point, and so you can definitely set up your relationship. Okay, and the different directions.
Thank you.
You're welcome. Any other questions? Comments? And if not, we can say goodbye for today. And so next week, I will be listening to you guys. Yes, you're gonna tell me beautiful stories next week, right? It will all be amazing.
Excuse me, is it
Yeah.
10? If it goes beyond 10 minutes, what happens?
Oh, you get 0. No, for individuals, so one person 10 minutes, two people 15 minutes total, the combination. I mean, try not to go over if you can. There is some little penalty, so meeting the time deadline is of course part of the rubric for evaluation, right? Because you have to do time management when you do presentations as a grad student. You may do presentations in conferences. You may do presentation, and it's important to try to be within the time limits as much as possible. Okay, um, so 10 minutes is 10 minutes, or 15 minutes 15 minutes. Try to stick to as close as possible, um, and most importantly, try to practice so that it comes in naturally. So next week, it's my voice will rest, and your voices are going to be the ones that are tired at the end of the lecture. I'm looking forward to it. I think I will have a pillow for my throat next week.
So it will be a bird view over the topics that you gave us, because in
Exactly.
10 minutes we cannot go into the details.
Yes. There's this quote. I've heard it attributed to Winston Churchill, but it might be someone else entirely, because you know how these quotes get attributed to people that never said them, right? But someone once said, was asked if he could do a presentation for a school for the end of the term, and he asked, how long will it be? And then they were asked, oh, does it matter? And the answer was, of course. If it's 1 hour presentation, I can go right now. If it's a 10-minute presentation, I need at least 3 weeks to prepare. So sometimes doing short is more difficult, right? Because you have to find what's important and cut away the fluff. Anyways, I will see you next week then. Enjoy the weekend.
Have a good night.
You too.